Okay, we're back once again, and we're computing the MLE for linear regression that we wanted to, right? So we formed this. We found that we needed to minimize this function of w to get the MLE for w, and we took the gradient, set it equal to 0 to find critical points, and then we ended up with this lovely expression here, nice and simple linear algebra expression, and we wanted to invert this A transpose A inverse. So if you know your linear algebra, then you may know that this A transpose A is invertible, assuming, so it's invertible if the columns of A are linearly independent. So let's assume this, and in order to be able to invert this thing, and so we'll assume this, so we can invert this under these assumptions, and we can solve for this w. So we get w equals this A transpose A inverse times A transpose Y. And this thing, by the way, let me just, as an aside, mention this quantity here, A plus, we usually, often it's denoted by A plus, or A dagger, is this A transpose A inverse times A transpose. And it's called the Moore-Penrose pseudo-inverse. It's a beautiful linear algebra thing. It's sort of like an inverse. It's sort of like the closest thing to inverting A in some sense. The problem A is not invertible because where's A? There's A. A is this design matrix thing, and this was there's n rows, so it's n by d. N by d because each of these, our input points was in d-dimensional space. And this isn't even necessarily a square matrix. So in general, this is not going to be invertible. So even though we might have liked to, the intuition is, in some sense, would have liked to, to solve AW equals Y for W, but we would have to invert A to do that, and so we can't do that. And the pseudo-inverse, so we could have written this expression here. This is equivalent to just, rewriting this using this new definition, the pseudo-inverse of A times Y. So that's the same thing. And so it's sort of, in some sense, the closest thing to inverting A, in a certain sense. Okay, so that's good. We got a critical point. And now let's see if we can show that it's a minimum. Or yeah, that it's a minimum. And that will show that it's a maximum of the log log likelihood, and therefore maximum of the likelihood. So to show that we have a minimum in a multivariable problem, we need to take the Hessian. So the Hessian is the matrix of second derivatives. So the Hessian, sometimes we write this way, of a function, or H, is the matrix of second derivatives. So, it's derivative with respect to the second derivative with respect to x1, and second derivative with respect to, well, I didn't leave myself space here. I'll just write it this way. Partial with respect to xi, partial with respect to xj of f. So the ijth entry of this matrix is this second derivative of f. Okay. Often we write matrices like this, this sort of notation. Okay, so let's compute this Hessian thing. So in order to do that, we need to compute the second derivatives, and we've already computed the gradient, so we're halfway there. And okay, so right, so there's a trick we can use here. So this gradient, or the Hessian now, of this L thing with respect to W is A transpose A. I claim that's equal to A transpose A because this, well, let me write it down here. I claim this is true because the gradient of L was the column vector of the first derivatives, and let's take the derivative of this with respect to, say, Wj. So this was, what was it? It was minus A transpose Y plus A transpose AW. This is a constant with respect to W, so it's 0. And this is a combination of the columns of A transpose A with coefficients W. So this is W1 times, let me just say, first column of A transpose A, W2 times the second column, and so on. Whatever, Wn, I guess, or Wd times the dth column. So if we take the partial derivative with respect to Wj, we just get the jth column of A transpose A. And so the matrix of secondary, so that gives us the one column in this matrix, this Hessian matrix, and so it gives us the jth column, in fact. This is the jth column of A transpose A, and it's just the jth column because this is, well, just by the definition of the gradient is the column vector. So this is partial with respect to Wj, partial with respect to W1, and so on. Partial with respect to Wj, partial with respect to Wd. And that is the jth column of this matrix, or the jth row. I mean, it's a symmetric matrix, so I guess the way I wrote it, it looks like the the transpose of the jth row or something, but it's a symmetric matrix. So this is also the jth column, and so it's equal to the jth column of A transpose A, and that holds for all columns J, so we get this result. The Hessian is A transpose A. And now we wanted to show that the Hessian, so to show that it's a minimum, we need the Hessian to be positive semi-definite. We would want it to be strictly positive definite to guarantee a unique minimum, but for it to be a minimum, we just need it to be positive semi-definite, and in fact, A transpose A is positive semi-definite. And so therefore, this solution, well, we got it here. W, this critical point, well, it was the unique critical point, right? So and since this is a positive semi-definite Hessian, that means that critical point, well, this is the Hessian at any W, really, and so in particular it's the Hessian at that W, and so that implies that W MLE, let's put this in a good, something green, that's good. So W MLE equals this pseudo inverse times A. So let's write out A transpose A inverse times A transpose times Y. Right? It's the MLE because it's the minimizer. Back up to here. We minimized this function L. This is a function of W. And minimizing this is the same as maximizing, if we include the minus signs, maximizing minus that, and the constant makes no difference. And maximizing that is the same as maximizing e to that, because e is order preserving. Right? E is like, it's like this. So x less than y implies e to the x is less than e to the y. And this is just a constant again. So minimizing this is the same as maximizing the likelihood function, and that is what we wanted to do to get the MLE. We wanted to find a maximizer. And in fact, it's equal in this case. There's a unique maximizer. And it equals, back down here, where is it? Equals this beautiful, beautiful quantity. So in the course of doing this, let's just point out a couple of things that so that's our solution. And a sort of interesting, well, one little byproduct we got here was these nice facts about the gradient of, so these are nice little tricks to use when you're working with gradients in linear algebra. The two tricks that I used here, I guess I wrote them here. These two tricks. So those are some nice little tricks that you can use. And also a more general interesting thing here is that this L, remember L, we also could have, it was equal to this dot product, but that was just equal to the square of the norm. So let's go back down here. So L was 1/2 y minus a w. L was, it's a function of w squared. And we minimized this with respect to w, had a unique minimizer. So minimizing this is the same as, that's the same as minimizing just the norm, the square root of that. This is the Euclidean norm. This is the Euclidean distance between y and aw. I'll just put it this way. D is the Euclidean distance. So this w that we solved for, this is it's the w that gets you as close as possible to y. So this is a very intuitive interpretation of what the MLE is doing here, and more generally what the pseudo-inverse does. The pseudo-inverse, remember we talked about how, in some sense we might have liked to solve this, aw equals y, but we can't. We can't because, well, in general we can't because y might not be in the span here for, the possible values this could achieve. But what the pseudo-inverse does is it gets you as close as possible. It gives you the w that gets a times w as close as possible in Euclidean distance to y. So that's a nice intuition for what this is doing. Alright, so that's it. We got the MLE for linear regression, and you could use this, you could plug this into the formula, and that would give you the function to predict, as we talked about.